Thank you for introduction. It's okay? Enough? Thank you. So this is a joint work with Naoyuki Shinohara from NICT and Takeshi Shimoyama from Fujitsu Laboratories and my supervisor Tsuyoshi Takagi from Kyushu University. Okay, so this is a press release from Fujitsu Laboratories. Do you know this? Anyone? No? Thank you. Okay, so this already press released in June, I think so. This year's June, and okay, so our work is solving the discrete logarithm problem of GX3 to 6 times 97. This is related to the Paring-Based Cryptosystems or iterative pairing of ternary case. So previous record for this ternary field is 676 bit size. This also achieved by our groups. And this is broken in December 2009. And our achieved record is more big, very bigger than that, 923 bit size. This is n is equal to 97. So it is broken in April 2012. So this is the outline of my talk. Firstly, I introduced the security of Paring-Based Cryptosystems or using iterative pairing over GX3 to n. And then I introduced the function field sieve, which is I use algorithms, and this is asymptotically the fastest method for discrete logarithm problem over GX3 to 6 times 6 ternary field. And then I'll report my experiment results, and finally rough estimation and conclusion I report. This estimation is very rough, but I think it's enough precise. So okay, let's start. Firstly, I introduce iterative pairing of GX3 to n. This is defined by this curve. This curve. And this is very basic, not basic explanation, very rough. So iterative pairing is G1 to G1 to G1 and G1 to G2. And G1 is the prime over subgroup of point group of elliptic curve over GX3 to n, and G2 is prime order subgroup of GX3 to 6n. And G1 and G2 has the same order. And also important property, binarity. This is very important. So next. Okay, so security of Paring-Based Cryptosystems is proved using several number theoretic problems. Barnier Diffie-Hellman, Strong Diffie-Hellman, any other Diffie-Hellman problem. But the most important problem is discrete logarithm problem, because their problem can be reduced to discrete logarithm problem. So we need to estimate the complexity of this problem. So in pairing-based cryptosystems, we should estimate the two discrete logarithm problem. And now I consider about G1. Then G1 is on the elliptic curve, so discrete logarithm problem of G1 is ECDLP. Of course, maybe you know. So, a given point Q and P computes the integer S such that Q equal SP. This is ECDLP. So, but there is pairing, so we can transform to the discrete logarithm problem over GX final field. So compute ET of PQ and ET of PP. Then there is such a discrete logarithm problem. ET of PQ is equal to ET of PP to the S, integer S. So solving the discrete logarithm problem over GX3 to 6n, then we can solve the ECDLP on this side. So we should consider both sides for pairing-based cryptosystems. So now we introduce the attack algorithm for pairing-based cryptosystems. One is solving the ECDLP. This is also, you know that Polar's law is one of the most efficient algorithms. This complexity is square root order. So okay. So, but in discrete logarithm problem over GX3 to 6n case, then we can use the more efficient algorithm, function field sieve. So this is only efficient for small characteristics, and in large characteristics case, we can use the function field sieve. Each number field sieve should be used. The complexity of function field sieve is like this. It's sub-exponential. So now our target is n is equal to 97 case. So the curve is this equation, and order is prime, 151 bit prime, like this. So we want to solve about the DLP on G2, because DLP on G1 is very high complexity, 2 to 75. It seems to be infeasible. But the DLP on G2 is almost equal to DLP over the GX3 to 6 times 97, which has 923 bit size cardinality. So previous estimation is like this, 2 to 71, which is estimated by Joan Garcia in 2006. But this is estimated asymptotically. So in such certain case, it is not precise, I think. So this is precise enough? Maybe not, I think. So now I introduce function field sieve. So basic idea is that construct two function field, and each function, over each function field, we define the factor base, the set of elements, special elements, and then make a relation between logarithm of elements of factor base, and solve the linear system. Then we can obtain logarithm of elements of factor base. So we select bivariate polynomial H1 and H2, and which satisfy certain conditions. But certain conditions is too many to introduce in this talk. So usually, degree of H1 on Y is equal to 1, and degree of H2 on Y is larger than 1. So H1 side we call rational side or linear side, and in this talk we call rational side. And H2 side it calls algebraic side. Okay, so this is the overview of the function field C. So it consists of 4 phases. Firstly, select polynomials and parameters and important element sets, factor bases. And then correct the relation between logarithm of factor base and logarithm of elements of factor base, and solve the linear systems constructed by such relations, and then obtain logarithm of elements of factor base. And finally, of course, the target element is usually in the factor base. So we should compute the target element, logarithm of target element. So in last phases, we compute the logarithm of target element using the logarithm of elements of factor base. So now I explained primary section, and next is correcting relation and linear algebra and individual log. So in polynomial section we use polynomial section method, which is proposed by Jules in 2006. And we fixed the H1 and H2 as this form. And there are many parameters, but we introduce important parameters only. So kappa, this is extension degree of coefficient field, selected from 1, 2, 3, and 6. And dH is degree of H2 here. And dm is degree of mx, this degree of this polynomial. And B is smoothness band. This is this used for defining of the factor base. So R and S is used for next phase, correcting relations. And we define the factor base like this. So rational side is rational factor base. Rational factor base is the set of irreducible polynomial of degree not larger than b. And algebraic factor base is the set of small prime divisors of degree 1. And now I introduce our optimization method. So as I said, previous works is estimated asymmetrically, so complexity is very high. But our work is estimated more precisely. So especially specialized to our case, so GX3 to 6N, and consider the Granger's smoothness band. This is sorry, I can't say in easy words. This is Granger's smoothness band is not used for the experiment, but used for the analyzed complexity. And free relation is the relation obtained without computation, and Gauss action is a method for compress the variable of linear equations. And the relative and large prime variation and the filtering is famous in the number field sieve. It is described later. And then our estimation is, complexity is 2 to 53. It is very reduced. And 2 to 53 may be not infeasible, can be breakable. So we work on this. And parameter we choose is like this. Kappa is 3 and DH is 6, DM equals 33, and BRS is 6. So here I introduced the correcting relations phase. So in this phase, we correct many B-smooth pairs. So B-smooth pairs means satisfies these conditions. So important conditions are R should be monic and Rm plus S is B-smooth, and this polynomial is also B-smooth. Then each B-smooth pair, we obtain the relationship between the logarithm of elements of factor base, like this. So then we correct many B-smooth pairs. Then we can construct linear system constructed by the relation of this. Then solve the linear system. Then we can obtain logarithm of factor base. Okay, so now we introduce the lattice sieve. Lattice sieve is one of the most efficient sieving. So sieving is how to say the method to find the candidate. Candidate means that it's B-smooth in the high probability, not low probability. So with sieving, we only output the candidate, and then we factorize the candidate and check the B-smooth or not. Of course, again. We can check by the all RS pairs, which is B-smooth or not. But it is very, very not efficient. So bad strategy. So firstly, we find the candidate, then B-smooth or not, check the B-smooth or not. So for introducing the lattice sieve, we define the set of this such a set. This is similar to the factor base. So if we define such a set, then we can find the divisor factor, prime factor of this polynomial easily without factoring. So for example, RT plus S equals 0 modulo P, then Rm plus S is equal to 0 modulo P. When Pt is in this side. So then Q is for Q. This is called the special Q. Sieving is done on this RS. So where R1, S1, and R2, S2 is reduced lattice basis of this. Then the Rm process or this polynomial of this Rs is divisible by this Q. So then we're saving on this CD plane. So from Rs to transform to the CD plane. Then on such CD plane of degree upbounded by capital C and capital D, such CD such that Rm process and this polynomial is divisible P. But this P is in this set. So SR is called the saving factor base, so rational side. Saving factor base in rational side. And this is in algebraic side. Then in lattice sieve, we compute this CD pairs. So C0 plus Kp and D, and C0 is computed by this. Then Rm process or this polynomial of CD is divisible by P. So if we compute this polynomial for all PT, then we can know the factor of Rm process and this polynomial without factoring. So this is very important. And this is our representation of this element in our implementation. Because the BRS is 6, bounded by 6, so the degree of elements we treated is upper bounded by 6. So it means the degree is smaller than 8. So we use this representation. Kappa is equal to 3, so we need we need 3 GX3 element. So GX3 is represented by 2 bits, so high bit and low bit, and this is 3 elements, so high bit, low bit, high bit, low bit, and high bit, low bit. 3 elements of the GX3. So this column is this column represents the 1 element of GX3, GX3 to 3. And row is bit size, and this 8-bit is 8-bit represents the GX3 to 3 polynomial ring of GX3 to 3 of degree smaller than 8. It can be represented. So we now consider the SSE register. It has 128-bit size. So it means 6 registers. We use 6 registers, then we can treat the 16 elements of polynomial ring of GX3 to 3. This means 16 elements are computed at once. So this we call the SIMD implementation. Maybe it is not most efficient because it uses many registers. but I believe it is enough to enough efficient. And more, I introduce our improved for our case. Maybe let's see. So, as I said, R should be monic for efficient computation. This means if R is not monic, then the factorization is not unique up. So R should be monic or fix it as a constant. Not constant, sorry. Constant of R should be fixed. But if R is monic, then it is difficult to fix in lattice sieve, because in lattice sieve R is represented by this base. So R is CR1 plus DR2. So if we want fix to monic, then we need many branch and many degree aberration. It is not efficient. So we transform R is monic to constant term of R is 1. And then modify the reduced lattice basis so that R1, constant of R1 is 0 and constant of R2 is 1. And the shaping is done with constant of B is 1. This is not any branch, not any degree aberration, so it is efficient. And other optimization is like large prime variation and omitting the degree omitting the shaping of degree 1, but it's not technical, so I skipped the explanation. But important our improvement is that this classification of shaping of degree 5. I introduced this. Next slide. So we shaping the degree of 2 to 5, but 5 shaping of 5 is much slower than the others, about 10 times or more. So we want to accelerate this shaping. On the other hand, we fix the special degree of special Q is 6, and so reduce lattice basis of degree of reduced lattice basis is about the 3 in most cases, because degree of special Q is 6. So capital RS, so degree upper bound degree upper bound of RS is 6. Then so degree upper bound of C and D is 6 minus 3. Minus 3 is because degree of R1, S1, R2, S2 is 3. So capital CD is 3. This capital C and capital D is upper bound of degree of C and D. And degree of C0, C0 is computed by this polynomial, becomes 4 because P is degree of P is shaping. Degree of P is 5. This 5 is equal to 5 in degree of P, and upper bound of C is 3. So most of cases degree of C0 is 4, and it is not. It is very waste for me, for us. It is waste of time to compute. So we want to compute with degree of C0 is less than 3 only. So how to do that? So it is very easy in the mathematics. So if the coefficient of the fourth order term of C0 is 0, then it has a degree of 3. So how is the condition of the degree of C0 is 3 less than 3 is occurred. So now let alpha I be the coefficient of the fourth order term of this polynomial. And because degree D is less than 3, D is represented by this form. So the coefficient of the fourth order term of C0 is equal to D3 alpha 3 plus D2 alpha 2 plus D1 alpha 1 plus alpha 0. So if it is equal to 0, then the degree of C0 is less than 3. So solve So if D1 is satisfied this condition, then degree of C0 is less than 3. Because if D1 is sufficient, satisfies this form, then the coefficient of the fourth order term of C0 is 0. So in such case, if alpha 1 equals 0 and k equals 0, k is this form, then C0 should be computed by any D1, because D1 is any element. But if A1 is not equal to 0, then C0 is uniquely determined for given D2 and D3. So we can ignore about 226 D1s. This 26 D1 is not satisfying this condition. So this is very easy in mathematics, but this improvement makes over 10 times faster. It is very important in practical. So next, after the lattice sieve, we get the candidate, which is bismuth with high probability. So then each candidate we check it is the smoothness or not, bismuth or not. To check it, we use the smoothness test. So smoothness test is very easy. So if this equation is hold, then U means this polynomials. U is bismuth in high probability. But we have too many candidates, like a billion or more. So we should make the faster. We should make this computation faster. So computation of this computation, main computation part of this is modular cubic. So like this, like this. If A is polynomial, then cube of A, take the cube of A, then reduction by U. But in ternary field, cube is very easy. So the problem is reduction. But it is a linear cubic. So in ternary field, this equation is false. So reduction is computed by reduction can be computed by just table lookup. So table lookup is better than reduction in our case. So now the problem is how to develop the table, because U is input, so each input we should compute the table. But this making the table is very easy. Just one reduction of this polynomial. So in smoothness test, we treat very big degree, so bigger than the lattice case. Lattice case, we treat very small degree. It is degree smaller than 8. But in smoothness test case, it is more larger. So we represent this representation for the smoothness test. The feature of this representation is the separate the coefficient of odd degree and coefficient of even degree are separated. Since the bit shift of for all 128 bits is cannot compute in one instruction, so we want to remove this instruction. So we separate like that. Then this instruction is necessary, not necessary. But this representation is also the most efficient, I think. There is probably more efficient representation. Oh, sorry. So this is the effect of our improvements. So first implementation is use the lattice 4006 FFS and SIMD and large prime variation. SIMD is 60 elements. We use this 60 elements at once. So in this implementation, estimated days for collecting relations is about over the 350 days. This is very big problem. So we improved our implementation using the classification. Then it is reduced to 100 days. So we continued improves our implementation, and finally the estimated time is about 50 days. It's reduced to 50 days. So from initial implementation, we accelerate about 7 times more, 7 times faster. So now I introduce the linear algebra phase. This is solving the linear systems or this moduli. So a feature of matrix is large and sparse, and each non-zero element is small, very small. I write at most 8 bits, but more smaller, about 3 bits or 4 bits. But I'm not sure. So I write at most 8 bits. And the computation was done modulo prime 151 primes, because our goal is not solving the discrete logarithm problem, discrete logarithm problem of GF3 to 6 times 97. Our goal is solve discrete logarithm problem of G2. G2 has order of prime 151 prime. So we use this module. And firstly, we use the Gauss action to compress the variables of linear equation, linear systems. So this is, so firstly, select the F is for construct the final field of GX3 to 6 times 97. But the coefficients of all coefficients of this polynomial are in GF3, not GF3 kappa. So it means the coefficient is, all coefficients are in the 0, 1, 2. So then for this map, x is fixed. So there is a relationship in the logarithm of element of factor base we can construct. Because x is fixed, so if we apply the phi to the factor base, so for example, irreducible polynomial of degree b, then phi of that polynomial is also degree of b, but coefficient is changed. So there is the relationship between the factor base. And if we use the Gauss action, so kappa variables can be compressed to one variable. So we can reduce it to 1 over kappa. We can reduce the number of variables to 1 over kappa. But the problem is each non-zero element becomes larger. So each non-zero element can be represented by this form. But it is not crucial problem, because we can the important information is only EI. This is not important. So store as EI only instead of integer E is a good strategy. So in our case, we chose the kappa as 3, so we store just triplet E0, E1, and E2. And then we use the filtering. Filtering is one of the partial triangulation, like this. Can see it? So this is the partial triangulation part, and this is sorry, I can say. Okay, so just triangulation partially. And then we solve the partial or reduced linear system. This is the main part of the linear phase, linear algebra phase, and we use the Lanczos method for this computation. And then we solve this reduced linear systems. Then we can get this solution by backward substitution, like the Gaussian elimination. So finally, last phase, individual logarithm phase. So after the linear algebra phase, we got the logarithm of factor base, logarithm of elements of factor base. So if we can represent the logarithm of target element to the sum of the logarithm of elements of factor base, then we can solve the logarithm, discrete logarithm problem. But this is, but for arbitrary generator, so if G is in the factor base, then there is no problem. But if G is not in the factor base, it is a problem. There is a problem. So because we don't have the logarithm or base of arbitrary generator. So for arbitrary generator, we compute the two individual logarithms. So one is log G of t, log GT, and one is log G of G0. G0 is arbitrary generator, and G is generator in the factor base. Then compute the change base. Then we get the logarithm of target elements on arbitrary generator. Also, this computation also was done in modulo prime 151 bit order. So individual logarithm phase has two phases. One is rationalization and two is special Q descent. So rationalization is sum of randomization phase. So for target element T, gets the integer gamma and G to the gamma times T. Compute the G gamma times T and rationalize like that. Then Z1 and Z2 has a degree of half of degree of F. Then find the M smooth, that M is larger than P. M smooth elements of Z1 and Z2. So then, but now, if we have the M smooth element, we can't compute the logarithm of target element because there is logarithm not obtained yet. So to compute the logarithm of element which is not computed yet, so we use a special Q descent. This is using the special Q techniques, and then compute the relative, like the correcting relation phase. So for example, for P, P is not in the factor base, so we should compute this logarithm. So choose P as a special Q and find this relation, like this relation. But Pi and Pj, there is a limitation. So degree of Pi and degree of Pj are smaller than the degree of P. And if degree of the Pi or degree of the Pj are still larger than B, then we choose this Pi or Pj as a special queue and compute like a relation repeatedly. Then the degree is decreased in each steps. So finally, it reaches degree B, degree smaller than B, and it is already obtained the logarithm. So, how much? Sorry, sorry. But in English, so experiment results important, but it already published in the ePrint. So, if you are interested in the experiment results, please see it. I skip it. Sorry. Sorry. So, estimation and conclusion. Estimation is very important because I think so. I want to spend of time in the estimation. So, estimation is our estimation based on the experiment and based on the just analyze the complexity is here. Previous work is for n is equal to 97, then previous work is about the 71 bit security. N is equal to 193, then it has 80-bit security. And for 509, then it has 128-bit security. This is the previous work. And based on the complexity, analyzed complexity, the 97 is about 53-bit security, and 193 has 91-bit security or 92-bit security. And 509 has 111 security, very reduced. So, but based on experiment, the 97 has 97 is 2 to 63 clock cycles to solve the discrete logarithm problem. And for 193, it is 2 to 82 clock cycles. And for 509, it is 521, 2 to 521 clock cycles. So, but this is very rough, but I think it is enough to precise. So, this means difference between the complexity and clock cycles is so based on the implementation, because complexity in the complexity side, the unit is very expensive in implementation, practical. So this is there is a difference about the 7 clock cycles. One unit is equal to 1,000 clock cycles. And compared to this, compare note. So this is how many security this is. For confirm this security level, I introduced the Sequoia and K computer, supercomputers, K and Sequoia supercomputer. So Sequoia has 16.3 petaflops, and supercomputer K has 10.5 petaflops. This means 2 to 78 flop years. And K computer has 2 to 70, also 2 to 78 flop years. So if we can assume that one clock cycle is equal to one flop in the supercomputer, then we can break the parameter n is equal to 163 if we can use supercomputer K or Sequoia for a year. So conclusion. So we can solve the discrete logarithm problem over GX3 to 6 times 97 in 148 days using a 250 CPU cores. But it's not fully discrete logarithm problem over the GX3 to 6 times 97. We just solved the discrete logarithm problem over G2. G2 has group order 151 prime 151 prime order. It's not the same, but almost same. So about the future work is we estimate about the GX3 to 6n, but there are many embedding fields related to the Paring-Based crypto, like the GF2 to 4n, GF2 to 4n, and GFP to 10, and GFP to 12, and so on. So maybe GF2 to 4n is almost equal to our case. So it is comparable, compatible. But GFP to 10 or GFP to 12 is very different. So we should work on this kind of fields. Okay, thank you for your attention, and sorry for my poor English.
Thanks for the talk and for keeping on time. Are there any questions?
Hi. Is there any reason why you chose that particular polynomial?
Sorry?
Is there any reason why you chose that particular polynomial for the function field, the y to the 6 plus x?
No.
Oh.
There is no. I think it is efficient, but I didn't consider other polynomial.
Okay, so the usual rationale is to use a function field which actually corresponds to a curve which has many points over small extensions.
Yeah.
So this one does not. So possibly you could have obtained an improvement by choosing another polynomial. I mean,
sorry.
It's possibly something to check.
Thank you.
Could you please show us the slide that you skipped?
Sorry? Sorry?
The question, I guess it was more a remark. It was about all the slides that you skipped. I don't think
sorry.
you have time to go.
Experiment results. This is a target problem. So we use pi and e to set the target problem, our target problem like this. So point q pi is from this form. So this is a tunnel representation of the pi, and this is tunnel representation of e. and then embed to the polynomial ring and compute the Q pi and QE. It is the point of the supersingular elliptic curve. Then our target problem is this: solve ECDLP of Q pi is equal to SQP. So this is the from it using ETT pairing, we can embed this problem to the DLP of the finite field. So this is a result of the coordination space. So now our number of required relation is about 100 million over or more. But there is many free relations in our finite fields. So especially 1 over 4 of these required relations. And for each special Q, we took about 400 seconds. And each special Q, we obtained 65 relations. And we compute many special Qs. So 2.5 million. And this computation was done in this term. So it is 180 days, 18 days, including lost time due to the updating its code, power age. Stop the power. Power outage. Thank you. Power outage, because due to the earthquake in the Tohoku in Japan, there's a huge earthquake. So we should be in the power outage. There is a planned power outage. So if we exclude this lost time, then required time is 53 days. And now we obtain 153 million relations. It is enough to solve the linear systems. And then we go to the linear algebra phase. So firstly, we use the Galois to reduce the variables, number of variables. It reduces to 1/3. And more, then we use a filtering to reduce more. So in Singleton Creek, it reduced to 31%, and we use merging, especially 6-way merging. 6-way means delete the column whose weight is not larger than 6. Delete it. So after the 6-way merge, there are no column whose weight is not larger than 6. Smaller than 7. Sorry. So yeah. Sorry. So and finally, we obtain the reduced matrix, which has 6 million equations and 6 million variables. So this is a table of the estimated time of Paring-Based method after the K-way merge. So we conducted the 2-way merge to 10-way merge, and we use a 6-way merge. But there is a more efficient merge matrix. 8-way merge is the best choice, but we don't use it because it is a long story. So, so up to the 6-way merge, we use a server which has 16 gigabyte RAM. But in this server, we can't compute after the 7-way merge because the merging ran out the RAM, so we can't compute it efficiently. So after that, we have the opportunity to using the server which has a 128 gigabyte RAM. So we conducted 7-way merge to 10-way merge. Then we have found this good choice, but in that time we already started the next phases, so we can't use the 8-way merge. So this is the Paring-Based method, information of Paring-Based method. So we compute these terms. It is 90 days, including also lost time. So we use 21 PCs. So we divide the matrix to the 7 times 3 submatrix. And this computation required about 80 days. And individual logarithm phase, we compute rationalization. It took about 40 days using the 20 PCs. And this is obtained good smoothness polynomials, 30 smooth and 50 smooth, and 15 smooth and 40 smooth. And in special Q descent, it is very easy. Just 1 day for this computation. And log eta t of log g eta t of q pi qe is this integer, and log g eta t of q pi is this integer. So our target logarithm of our target element is like this. Okay, so this is this information is all including in the ePrint paper. So if you are interested in, then please read it. Sorry and thank you.